Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome back everybody. Please be seated. You can be in the back this time since we have a normal talk again with big characters. They're non-ASCII, as you may see already. Yes, the next speaker is from Turkey, Hüseyin Hisil, and he will speak on faster formulas for elliptic curves. So, a good title, I'd say.
Thanks, Peter. Thanks for the organization committee for the invitation. The title of this talk was fixed. It was determined pretty much time ago, but the slides finished just an hour ago. So now I would change the title to this one, A Roadmap for Formula Hunters. Because I will mostly be speaking of a way of deriving a lot of formulas and selecting between them, rather than just displaying formulas, which will not be so meaningful. And since everything here is done on computers, computer algebra, using computer algebra, let's be honest, this would be a better title, I believe. Okay, for an hour talk, I have a very simple outline. In the first half of the talk, I will be talking about how we can make the life easier for deriving addition on elliptic curves, any kind of elliptic curve. And in the second part, we will be looking at some timing results, operation counts sort of thing, implementational stuff. And I'll start with explaining the motivation of this research. I think it was back in 2003 or something, when I was a freshman, I first came along, I first learned about elliptic curve cryptography, and I asked the instructor why we have to use Weierstrass curves in elliptic curve cryptography, and the answer was, it is a standard choice. And the answer really didn't satisfy my needs, and I go there and find out these classic papers. I'm sure you're very familiar to these papers. What is all common on these three papers is that the result always motivates you towards using the Weierstrass form of elliptic curves. Because at those times, with the formulas that we know, these Weierstrass form curves were really the fastest ones once you use the Jacobian coordinates. But after I saw these three papers, I said, okay, they are the fastest. I'm not going to go through that direction. I don't want to look at the addition law anymore. But later on, around 2003, I saw this paper, and this paper was actually written for a different topic. This is about side channel attacks, preventing them. But at some portion of the paper, the authors claim that their formulas for the Jacobi form can be faster than the formulas for Weierstrass form. And still, I wasn't that concerned about the topic, but it was the start of the motivation. And from this date, after 2007, there has been other papers appeared, and finally, the sparkling bit came with the introduction of Edwards curves to the committee. And Edwards curves solidly broke the speed limit of Jacobian coordinates at that time. So I said, okay, this is the motivation for me. Probably there's more things to dig out there, so I will try to concentrate on this topic. Over 3 years, I looked at these 5 famous curve models, and for each of them, I was lucky enough to come along with a concrete result. And along the way, I also checked many more elliptic curve models for efficient group laws as well. I even tried intersecting hypersurfaces until I get a curve, until I get a elliptic curve, and looked at group laws on such kind of objects. But these 5 are still the fastest ones, if you believe me. And it would be possible to give examples for all of them, but it's only going to complicate the talk. So I will giving examples using only the Jacoby quartic curves. So at the end, I will also be mentioning the outcome for the other 4. So I'll start with giving some basic properties of Jacoby quartic curves, just to remember. So this affine curve is called Jacoby quartic curve, and this affine curve is non-singular provided that the delta is non-zero. The usual projective closure is given by this homogeneous projective equation, and unless if z is not 0, a triple corresponds to the affine point in the usual sense. I gave this to show the weights of the coordinates. And there's only one point at infinity. It is this point, and this point is singular. And if we resolve the singularity here, we end up with 2 more points. I wrote them down as omega 1 and omega 2. And the minimal field of definition for these 2 points are a field which contains the square root of the curve constant d. Of course, this extension can be k itself. So if we select a field containing the square root of the point set can be defined in this fashion. Here I will really abuse the notation. I hope algebraic geometers can forgive me. I will add these 2 points, omega 1 and omega 2, to my point set and call this L rational points over the curve. And once we have this curve is birationally equivalent to this Weierstrass curve given below via the maps below here. And we will have a very quick look at the properties of these 2 maps. To satisfy the birational equivalence, we can trivially check that the composition of the maps gives identity maps on the relevant curve. And if you look at the problematic points, we can easily say for the first map that if we have x equal to 0, we have problem. We say that the point 0, 1 on the Jacoby quartic curve, at that point, our map phi is not defined. It is not regular. And it is regular at all other points. There is another point which is 0 minus 1. And at first glance, it might seem that 0 minus 1 is also not regular, but actually it is, because these maps are actually elements of a function field, so we can always find alternative representations for these rational expressions. And here is an alternative map, and using this map I can always map 0 minus 1 to the point 0, 0 on the Weierstrass curve. Let's look at the other map, that is psi. For psi, we have problem again whenever we have v equal to 0. There are 3 such points. And before stating which ones the map is not defined, let's see that 0, 0 can be sent to the previous curve, to Jacoby quartic curve, to the point 0 minus 1 with this alternative map here. And the remaining 2 points with v coordinate equal to 0 actually corresponds to the points at infinity, omega 1 and omega 2. And from this time on, technically, although Jacobi quartic curves are not elliptic curves, I will treat them as elliptic curves by adding that omega 1 and omega 2, and I'm not going to mention it again. An interesting property is that psi becomes a morphism whenever d is non-squaring k. That is, you can take all points to the other side, because the points at infinity are only defined when d is a squaring k. If it is non-square, then we don't have points at infinity at all. Reversely, I can say that this Weierstrass curve is birationally equivalent to this Jacobi quartic curve, extended Jacobi quartic curve. And we very well know that this Weierstrass form elliptic curve covers all elliptic curves having at least one point of order 2. Therefore, since they are birationally equivalent, we conclude that Jacobi quartic curves covers all curves of even order. And it is well known that approximately 2/3 of equivalence classes fall into this category. So the overview is done. The next question now is, what is the addition law on Jacobi quartics? The answer is no. The answer is not new, but I will explain it in an alternative way, in the way I did in my research. So I used a lot of computer algebra to automate the group law, and my motivation was to find minimal degree expressions for addition law and prove the minimal degree whenever possible, and also look at other slightly higher degree formulas as well, in case they might be useful. And along the way, I also checked the formulas with computer software, and also I applied techniques to find alternative ones. So this is the backbone of what I used very frequently. So if we have two curves W and M defined over K, and if these two are, we assume that these two curves are birationally equivalent, and we have explicit maps phi and psi. And once we resolve the singularities, if we have one and have the distinguished point, which will later act as the identity element of the group, I let plus W be a map defined from this variety to W be the addition map on W, and I seek an answer for the addition law on M, and that is given by the composition of these maps here. And the answer is this map plus M is regular at all but finitely many points on M. This is rather an observation. So here is a numeric example, again using Jacobi quartic curves. So we had these maps defined already. So these are the curve constants and their relation to the Weierstrass curve. This is Jacobi quartic curve. This is the previous map I displayed, and this is the inverse map. Okay. We very well know the addition formulas for the Weierstrass curve, this one. And what remains is just to make the composition. Once we do the composition, we got a map defined from M to M, M cross M to M, and which describes the group law on this Jacobi quartic curve. And this map is regular at all but finitely many pairs. Okay, the map is not that cool, I know. We'll come to that point. I was actually lucky to fit everything in one page. There are really worse ones. Okay, the next step is we at least have something in hand that works. That is something. But the next thing is to simplify these algebraic expressions. And I was so lucky that there was a solution out there, which is a more general solution than I need, and which perfectly needed my needs, satisfied my needs here. And the algorithm is called the minimal total degree algorithm of Monaghan and Pierce. It was from 2006, so it is not from too long ago. And the idea goes like this. Let me explain it in a very brief way. So what we see here is the composition of maps, and I didn't expand the algebraic expressions. Otherwise, it's going to be some hundred pages long. But just assume that you do that computation and get the numerator and the denominator as polynomial expressions. So, and we write them here as n and d. N is numerator, d is denominator. So what this algorithm does is actually substitute lower degree polynomials as eta and theta, and tries to solve the resulting system of equations. And if a solution is not found, that means that you don't have any formulas that at that degree. So you have to look at higher degrees eventually. And once you find the solution, that is the minimal degree solution for you. The algorithm goes this way. But we shouldn't forget that this minimality is about the sum. I mean, I have the total degree for the denominator. I have the total degree for the numerator. I'm summing them up, and I'm trying to minimize this number. And the algorithm, this is why I write lazy bit in the title. It is it's already implemented, and an open source implementation is available in Pierce thesis. And if you run the algorithm, you immediately get these reduced algebraic expressions, which are much nicer than what I showed moments ago. And the credits goes to Chudnovsky and Chudnovsky, back to the paper from 1986. These algebraic expressions are actually found by them, with the slight difference that they use the projective weighted model, which is non-singular, and they place the identity at the point at infinity. That's the only difference. But basically, the algebraic expressions are just the same. The only difference is things like this numerator goes to denominator, denominator goes up, that sort of shuffling, nothing else. So this is the minimal degree addition formula for Jacobi quadratic curves. There's no other formulas. There are no other formula having lower degree than this. The algorithm actually proves this. But we can still have lower degree formulas and formulas which have degrees equal to this one. Here is one of them. I found this formula along the way. For computational purposes, these are actually affine formulas, but later we will look at the projective versions. This formula will be more useful for us because that term is reused here, squared, and there's a multiplication here. Here, on the first formula, it takes one multiplication more than what we need for the second one. So how did I obtain the second one? So here are the main core ideas. If we regard the map I give as addition formulas, and we immediately see that those distinguished algebraic expression by itself doesn't explain the group law, because there are special cases that we have to take care of. So solution might be finding other low degree formulas which might be defined for those exceptional cases. So let's take the denominator from the previous x coordinate here, this x coordinate, and let's take the denominator. If we think them as elements of this ring, defined, and the ring is defined over this field here, since the GCD of them is 1, the fraction doesn't really simplify further, or there is no, it doesn't simplify further than this in this function field. Now assume that n over d is a function on m cross m. So the curve equations, the relations that we obtain from curve equations will now come into play so that we can find alternative algebraic expressions for this. And if I compute, this is the main idea, if we compute this colon ideal, d plus k divided by n, and look at the reduced Grobner basis of this ideal, we will always see a minimal total degree denominator. This guarantees to have a minimal total degree denominator, but it doesn't guarantee to give us a minimal total degree formula itself, a fraction, as a fraction. But the denominator will be of the minimal degree. And most of the time, because we are using a graded monomial order when computing this Grobner basis, the degrees tend to get lower and lower in the generating ideal, the generators of your ideal. And if you compute this Grobner basis, you can find these elements inside as generators. And each one of them is a good alternative for being a new denominator. All you need to do is to look at the corresponding numerator for that algebraic expression. So let's pick up this one. There are other not so symmetric ones, but they can be fast. I really didn't check. As soon as I solved this one. So what we need to do is to compute this. This is not a polynomial operation. It's not a straightforward operation. It is a multivariate exact division algorithm. The first implementation also goes to this thesis, as far as I know. And if we compute the corresponding numerator for this x-coordinate formula, we get the alternative formula as this, with credits to Euler, who found this formula some hundreds of years ago. Okay, we can have a quick comparison between two formulas. They look different, but they do exactly the same thing. And if you're after obtaining more and more formulas, you can simply change the lexicographical ordering of your Grobner basis of the system. And that was the x-coordinate. And here are some more alternatives for the y-coordinate I found using such kind of ideas. And this is really a very short list. This list can go pages long, slightly increasing the total degree. And one of them is actually spotted by Chudnovsky and Chudnovsky. And what is interesting about these is that it doesn't depend on the curve constants. But for maximum speed computations, this formula is also not so helpful for us. I said that these maps, when considered as addition formulas, have problems. Let's have a look at those problems. So if I have two affine points, x1, y1, x2, y2, and I'm going to be adding these 2 points using these algebraic expressions, I say that if the result is a point at infinity, then the denominator is always 0. But the converse is not true. That is, once I substitute these coordinates, if I obtain a 0, it doesn't mean that adding these 2 points gives you a point at infinity. So we have to be careful here. So I set up the parameters here as usual, nothing really surprising. And the answer is just simple root solving here. I fix a point x1, y1. I exclude a special case where x1 is 0. I will mention why later. And I have the second point, x2, y2. That x2, y2, if that point is inside this set here, or I forgot to put the set notation, let's say sequence, one of the elements in the sequence, then this is 0. And these are all 4 cases. There are no other cases. And I really don't know now that which one of these ones led to point at infinity, which one of those ones led to an affine result. One of them is really interesting for cryptographers. That is this one. So it says that you can't use this denominator, the first formula, the minimal degree formula, for point doubling. You can't add a point to itself using this formula because you will immediately get 0 in the denominator. You can't divide by 0. You have a problem. And we need a solution. But we have a lot of those formulas. So if you look at this alternative formula, remember this was Euler's formula. This auxiliary part is due to Bill and Joa from 2003. And for this formula, the story is pretty much the same. I'm not going to tell it again. This should have been 1 minus the x1 squared, x2 squared. That's a mistake. In the same setup here, if you write them down, we'll see that the sequence, the analogous sequence for this denominator is different. And whenever this denominator fails for these 2 cases, I can always use the previous formula to cover those cases. And whenever the first formula, the minimal degree formula, fails for these 2 cases, I can use the alternative formula to cover those ones. But I have always a problem with these 2. Both formula fails at this part. And this is good news actually, because just by counting, I can say that these are points at infinity. Because I have 2 points at infinity, nothing left. It has to be. So the story is pretty much clear now. We are going to, with some more work, we will just put everything together into an algorithm here. In the start of the talk, I said I will treat the Jacoby quartic curves as elliptic curves. That's why I added omega 1 and omega 2 in the point set. And I enforce the existence of omega 1 and omega 2 by selecting a square, selecting the curve parameter d to have a square root in the underlying field. So the algorithm goes like this. It starts with a lot of if-then-else bits, which are basically corresponds to the 2 lemmas I just showed. The exception handling part is here. As you can see, if the first point is, let's say, omega 1, the second one is omega 1 as well. The output is 0, 1, and it goes in that fashion. And in some cases, the output is not a point at infinity. So we have simplified formulas for that coming from these lemmas. And these are only very limited number of cases. I mean, there are finite number of cases that we have to care about. The rest of the part is covered with these two formulas here. And what is nice about the second formula is that if D is non-square in K, we don't have points at infinity. And all of these branches just disappear. It's only enough to have these two lines. This is an analogous result, what we know for twisted adverse curves, for which the complete group laws were proved by Bernstein and Lange. And this is just an analogous result. And also what is nice about this formula is that I'm not going to give the theorem and the proof here, but if the point you're using, if the subgroup that you're using only has points of odd order, the denominator also never becomes 0. That is, it's again enough to have these two lines to at least have your arithmetic computed without any exceptions. And what is nice about the first one is that, again, if you have, if you are computing in an odd order subgroup, again, the only exceptional case that you will hit is going to be this one, the point doubling, the obvious case. You don't have to worry about other cases. So as long as you have special doubling formulas, you can use just two of them. For doubling, you use that special formula. It is not here. And for all other cases, you can use this minimal degree algebraic expressions. The total degree is, if we count here, for the numerator it is 2, for the denominator it is 2 as well. So the sum is 4. But for the second one, the sum is 6. That's why we call this one the minimal degree formulas. So this was the second part of the talk. Now we will have a very quick look at the inversion-free point addition, because for most implementations we don't like inversions. Inversions are really expensive. I'm a computer engineer myself, and I like implementation a lot. And for most implementations, if you write your code in C, most of the time inversion is not that expensive in comparison to multiplication. But if you optimize everything to its limit, things like, if you do things like selecting special fields with low Hamming degree, or if you do assembly optimizations, the IM ratio just goes up. I mean, inversion is really expensive. The best ratio I could hit in my implementations were 121. So 121 multiplications makes just one inversion. So in the rest of the talk, I'll assume that inversion is really expensive, and we always want to get rid of even from one inversion. So it is typical to use projective coordinates, some sort of projective coordinates in cryptographic applications, because it is they naturally eliminate the need for inversion throughout your scalar multiplication operation. In the end, if you need the result in affine coordinates, you can do the final inversion if you want. So for the Jacoby quartic curve that we just saw in this talk, I tried to count operations in difference when we embed our affine curve into some sort of projective space. Of course, there are infinitely many of them, but meaningful ones, according to me, are these ones. And if you do your operations in affine coordinates, then you always have to perform this inversion operation here. So I eliminate the first line directly. There are other cases where some of them appeared in the literature, some not. For example, this one is operation count in projective space. This is my operation count here. And if we sort them down, we see that the best alternative appears when we embed our curve over P3 in P3. So for a general addition, we only need 7 multiplications, 3 squares, and 1 multiplication by a curve constant for this curve when A is equal to -1/2. So this was the addition. Let's look at the doubling. I'm not going to write down the doubling formulas or the projective addition formulas. We'll just have a look at these operation counts. What is surprising here is that doubling, the best doubling that we can get, appears for the case homogeneous projective coordinates. So we have a kind of problem here because the best doubling is in homogeneous projective coordinates, but the best addition is in somewhere completely different than that. A nice observation here is that if I have a point which is a quadruplet here, x, y, z, x, y, t, and z, as soon as I discard the t coordinate, what is remaining, x, y, z, actually satisfies the homogeneous projective coordinate. So therefore, for practical reasons, I will think that coordinate t as an extended coordinate, as an redundant data that I have to carry along. In this fashion, I will be calling that sort of coordinate systems extended coordinate systems, and these ones as projective coordinates. So if you have implemented scalar multiplication before, you'll see that for variable p and k, you are trying to do key times p, where p is your point, k is your scalar, and both are variable. Then you will see that algorithm goes with multiple doublings. After multiple doublings, you do just one addition, and you continue with doing multiple doublings if you implement your algorithm in a windowed fashion. So these are a bit technical but this is the story. Same for all curve models. So what we do is, for all those repeated doublings, except the last one, we perform the addition. We perform the doubling here using the fastest formulas we have. As soon as I need addition, I will generate the necessary coordinate, that extra coordinate, on the fly. So once I do that, I will need another operation. Multiplication or squaring, doesn't matter. But actually, it is possible to do better than that. That is, we can finish that operation, that is doing doubling plus generating the extra coordinates in just 8 squarings. But still, this one is the fastest. So I do, for repeated doublings, I use this formula. But for the last one, I use this one. Now I'm ready to be able to use the addition formula here, because I have all 4 coordinates in my hand. I use this formula. What is nice here is that I really don't need to calculate the extended coordinate this time, because I'm going back to repeated doublings again. So although the addition here produces 4 coordinates for you, you only need 3 of them. Discard the t coordinate, so you don't really have to make 7m3 as 1D. It is actually 6m3 as 1D. And I just shift that extra squaring from here up to here, back, just to write the costs in a simpler way. So it is here at the last line. I will be explaining this one. These are basically the same slide from the same as the previous slide. The difference is that here I added the extended the mixed coordinates. So what I did in the previous slide was mixing homogeneous projective coordinates with extended homogeneous projective coordinates. I was jumping from one to each other all the time just to have my arithmetic faster. And I denote it by q to x. Q means quartic, Jacoby quartics. I didn't use j because it might have been mixed with Jacobian coordinates for Weierstrass curves. That's the reason. So the figure here tells me that for projective coordinates, I can do doubling in 3 and 4a or alternatively 2 and 5 as 7a. It depends on your implementation, the one which is faster. I have two set of formulas. Unified means the second set of formulas I showed with the denominator 1 minus d times x times x2, x1 times x2 square. That is a unified. That is called a unified denominator because it can be used for point doubling, and in the jargon, it is the first set of formulas is called dedicated addition formulas. Dedicated addition formulas are usually slightly faster than the unified ones. At least it has been this story for all curve models I studied so far. And for Jacobi quartic curves, the best coordinate system is the mixed coordinates here. So you only need that much of operations for doubling and this much of operation for effectively for additions. So Jacobi quartic curves, although I give examples over them, are not the fastest ones in most cases. We have adverse form. So these are a summary of literature results for adverse form and twisted adverse form. So E means homogeneous projective coordinates. These are the operation counts by Bernstein and Lange from 2007. And this I here means inverted coordinates, which was a surprise, removing a multiplication from addition here. And I considered other cases here. Again, this notation is similar. E stands for adverts, actually twisted adverts, and this E stands for extended coordinates. For this coordinate system, the doubling is slow. That's a problem. Addition is faster than the previous ones. That is good news. And what I do is I apply the same solution. I mix the coordinates. I jump from one to the other. I use the faster operation every time. So that is denoted x as extended coordinates. What I also find out that is if we use curve constant a minus 1 instead of 1 or some other value, we can further decrease the timings for addition. We need only 7 multiplication and 1 multiplication by a curve constant if we use the unified formulas for addition. And still we can benefit from fast doublings, as you can see here. And in the last bit, I found out dedicated formulas, minimal degree formulas, and these formulas can eliminate another multiplication by a curve constant here. So in total, you only need 8 multiplications for a general point addition. And further, if you are making, this is called in most publications as mixed addition. That is, if you have Z2 coordinate or either of these coordinates equal to 1, then it is enough to make just 7 multiplications. And so far, the adverse form have been the fastest for implementations, as far as I know. I have analogous results for Jacobi intersection form, that is representing elliptic curve as an intersection of two quadric surfaces. And for these ones, I have results here. Most of them are not documented in the literature, but you can find them in my thesis, which is available through my website. And that is quite interesting to remove a lot of multiplications here, as you can see. And doubling is as fast as doublings in Jacobi quartics and for Edwards. but still it can't beat Edwards. And the cubic form, Hessian form, is the most stubborn one for speedups. I really did a lot of crazy things, but I really couldn't manage a lot. The classical algorithm for doubling was 6M3S. I was able to find a 7M1S alternative and 3M6S alternative. Not a big speedup here. Similarly, for the conventional algorithm for addition requires 12M, but I was able to trade it with a lot of additions. One multiplication with a lot of additions here. And I have the extended version. Actually, I have two versions of this. One of them uses 6 coordinates to represent a point. Another one uses 9 coordinates to represent a point. You may say it's going to take a lot of place in your registers, but it is really nothing. It is just few bytes that you require. So with modern architecture, with desktop processors, it's really nothing to have 9 coordinates to represent your point, unless you have a very restricted device. And another stubborn model was short Weierstrass form. I really couldn't find anything faster, but I found unified addition formulas which are faster than the previous ones. And unified addition formula was not tried for Jacobian or Chudnovsky-Jacobian coordinates. I have also developed those formulas which are faster than the ones here we have for projective coordinates. And for a scalar multiplication where everything is variable, I can say that if we fix these constants, curve constants, when I started research, you will have to need to do this much of multiplications per qubit when doing the scalar multiplications. For example, for 256 bit, for each bit, you need to do this much of multiplications on average. And with the new formulas, they are shifted to these newer ones. What is nice here is that we were bounded to this efficiency back in 2005 and earlier. And now we hit these values, which are very, maybe not surprising, but I'm happy to see these values. And I believe that maybe in the future it will be possible to make them even faster. Here is an implementation. The source code is open for this implementation. You can download it from my website again. These are the cycle counts I measured on my PC at home. And these are the curve models. The parameters are selected to make them faster. And you need, using those newer formulas, you need this much of operations. This is just an implementation to compare the speed of different forms. It doesn't really target to make a new speed record, but this one is, at that time, was very close to the speed record, or maybe it was the best, I can't remember. But what is important here is that by simply changing, if possible, by simply changing your curve representation from Weierstrass to twisted Edwards, you can speed up your operations, decrease your cycle counts a lot. Thanks.
Okay, are there any questions?
Yes.
So, do you also consider using the Montgomery powering ladder to reduce the number of coordinates and speed up the multiplication?
I tried to work on that, but I couldn't have any success. Whatever is there out is the best. We have an alternative version came up in 2007 or something like that, using common surfaces. You can have a look at that. There is an explicit formulas database, which is the easiest way to find out those formulas. I really couldn't make them faster. But if you say they might be faster than these ones. I say it depends on the implementation. For some kind of implementations, you can make really nice assumptions or restrictions about the way you do arithmetic there, which can be competitive with these results. But I truly believe that these formulas, the fastest formulas for adverts, can beat Montgomery type ladders unless you fix some constant to 1.
What are the rationality conditions on
Can't hear, sorry.
any elliptic curve can be put in short wire stress form, but what are the rationality conditions, like having 4 torsion and 3 torsion?
Okay, all right. To keep it simple, I didn't really mention. So if you have a point of order 2, you can represent your curve in extended Jacoby quartic form. If you have 3 points of order 2, you can put it in a simpler form of Jacoby quartic form. It is this, I think it was the same story for Jacoby intersection form. If you have a point of order 4, you can write it in adverse form. What else? Weierstrass form covers all cases anyway. Yeah, I really didn't prepare those cases here because the way I'm looking at it is which one of those things are the fastest ones. Having a small torsion there, I really don't care about it as long as I have a big prime order subgroup which can resist all known attacks. The most important thing is the speed for me. I hope it's an answer.
Okay, if there are no further questions, then we reconvene at 4:45 and let's thank the speaker again.